Hi, welcome back to Algorithms. So today we're going to be using DP style ideas to solve one of the classic algorithmic challenges, the knapsack problem. And so we'll be thinking about the same version of the knapsack problem that we've looked at before, but now we're going to ask a very nuanced question. We're going to ask what subproblem structure in the knapsack problem gives us the information we need to solve this thing in an intelligent way. So let me refresh your memory about the knapsack problem. So we have n items of various values. So of values vi, where I equals 1 to the size of n. And throughout, I'm gonna variously refer to the size of the set n as either that using this notation with the cardinality bars next to the side or surrounding the set, or I can write the little n as well. So just note, if I write n, little n, that means the cardinality of big N. That'll be kind of my convention going throughout this thing. So we think of this capital N as a set, right? So n is the set 1, 2, all the way up to n. And each item in the set has a value vi. Each item in the set also has a weight, wi. So we also have weights in the set wi for I equals 1 to the size of n. Okay, and that should be very clearly a w. Yes, good. All right, we also are given a capacity, and I'll call that capacity big W. Non-zero, or it's greater than or equal to 0. It's non-negative. And we're trying to solve the following optimization problem. So solve optimization problem. We want to maximize the sum of the values of selected items. So maximize for I in some subset K, subject to, and so this is where K is a subset of N. So maximize the sum of the selected values, subject to. And so for those of you who aren't as familiar with kind of the optimization form of writing problems like this, we often take this subject to and abbreviate it just ST. So S, if you ever see ST, that means in an optimization problem, that means subject to. And that means now we're going to write down our constraints. Okay, so our constraints are, 1, implicitly, K is a subset of N. And 2, the more important one, is that the sum of the selected weights, so the sum for all I in the subset K, the sum of all the weights, Wi, is less than or equal to the capacity. Okay, and this is the one that ends up biting us as we go forward. So let's look at a particular instance of this problem. It's actually the same instance. Maybe there might be different indexing, but it's the same instance that we looked at when I very first introduced the knapsack problem. And we'll use this to kind of illustrate concepts moving forward. Okay, so here's a problem instance. Just a bit of language. You know, this above is the problem. Above that white line is the problem, right? I'm saying here is the general statement of what instances of this problem look like. But now when I plug numbers in for all of these things, I generate a problem instance, right? So it's a specific like chunk or object associated with this overall problem. If you like object-oriented programming, you think of like this as the class. And then, you know, here we're gonna instantiate the class. So we'll call this an object. That language is very rarely used in algorithms, but that's, if you're used to object-oriented thinking, that's what we're doing here, right? So what I'm doing now is I'm going to instantiate the problem. I'll create an instance of the problem, and what that means is I'm going to plug in numbers for everything. So I'll say my set of values is 42, 12. 40, and 25. And I really shouldn't be using curly braces here because this isn't a set, this is a tuple. right? The order matters. And so we can associate an index with each of these. And I'm going to one index this just for ease of language. So item 1 has a value of 42, item 2 has a value of 12, and so on. My set of weights is going to be 7, 3, 4, and 5. And so the way I read this is item 1 has a value of 42 and a weight of 7. Item 2 has a value of 12 and a weight of 3, and so on. And then my overall capacity, my big W, we could be careful and write bars on our capacity to differentiate that from the tuple of weights. The capacity here will just be 10. Okay, so we've solved this before. We solved this way back using an exhaustive search by writing down all the possible subsets. And we found out that the optimal subset is 3 and 4, right? Take the items 3 and 4. That's the best way to pack this knapsack. Okay, so the optimal subset, and I'll write this as K star. Okay, optimal subset K star is 3 and 4. And so what does that mean? Well, that means 3 is pointing to this object, and 4 is pointing to this object. And so that means we're bringing along this thing and this thing. And so what's the value of this subset? So value of K star is 65, right? 40 plus 25. And the weight of K star is 9. Okay, so we can kind of visualize this subset. Let's visualize this optimal subset actually sitting inside a knapsack. So what we can do is we can kind of draw the knapsack as a bar. Right, so there's our knapsack. So this has a total capacity of 10. So here's the knapsack. And our item 3 has a huge value, and it takes up a weight of 4. And so there's approximately our 4. So here's item 3. And then our item 4 has a weight of 5, so it fills up almost all the remaining capacity. So there's our item 4. And then there's a little bit of empty space in the knapsack. Okay, so this is empty space. Okay, so in our search for optimal subsets, or for optimal subset structure that would allow us to use a DP algorithm to solve this thing, we can think back a little bit to how we thought about this with the coin change problem. So in the coin change problem, we said, all right, suppose I give you optimal change, right, minimal change for some number, and then you take away one of the coins. What's left over? Well, what's left over is optimal change for whatever number is written down there, right? Whatever is left sitting on the table. So now let's think about what this thing would look like if I removed an item. So suppose I removed item 4 from what is written here. What would I have left over, right? So here's the kind of the notion. So what I'll do is this is a subtle difference from the change problem. What I'll do is I'll remove item 4 and its associated capacity. Okay, so what I'll do is I'm going to slice the bag right here, and I'll take this and I'll discard. Okay, so that's the kind of the visualized thing that I'm doing here. So what I'm doing is I'm saying, let's remove item 4. Remove item 4 and associated capacity. And then see what I have left. Okay, so I can draw the picture quite easily. Okay, so the picture is looks like this. Here, I should try to even draw it to scale. So go up to about there and there. So here's now item 3. Here's 1 unit of empty space. 1 unit. And so now we can ask, what is this? What am I looking at now that I have this kind of notionally smaller knapsack that just has item 3 in it? Well, you know, this is a weight of 4, right? So the weight here is 4. The W3 is 4. My capacity of this subproblem is so I'll call it my capacity prime is 5. And so let's think about what this represents. So if I have a knapsack with capacity 5, we could ask, what is the optimal subset of items 1, 2, and 3 that fits into this knapsack? Okay, and it doesn't take too much time to think about it to see that it has to be just the item 3. So suppose, looking now at this problem definition right here, this instance, suppose my capacity is 5, right? So I can only fit in something of 5. And suppose I do not have access to item 4. Then what can I do? Well, I only have 2 options. There's only 2 feasible subsets. I can only either put in just item 2, right? Just item 2 by itself would fit in a bag of capacity 5, and it would give me a value of 12. Or I could put in just item 4. Or sorry, just item 3. And just item 3, because it has a weight of only 4, would fit in a bag of 5, and it would give me a value of 40. Item 1 doesn't fit in a bag of 5, of capacity 5. Right? So the only things I could possibly do, if I'm looking at items 1 and 3, and my capacity is 5, is the only things I could do is I could put in 2, or I could put in 3, and 3 is the better value. So that's the optimal subset. So now let's look at what we have. If we go back to this sort of constrained problem, this sub-problem, if you will, let's describe clearly what this is. So 3, I'm going to write this down like this. 3 is the optimal subset and I'll say among items 1 through 3. 1, 2, 3. When the capacity is 5. Okay, so I've written this down here. Now let's go back up to the first question we asked and write that in this format. Okay, so here what I'll do is I'm going to insert a bit of space right here, and I'm going to write, and I'm going to describe using the same exact language. I'm going to describe this solution and say what is this solution and what is it a solution to? Like what is this solution optimal for? And so what did I write? Well, I named the subset, and then I said that and then I described the problem that it was optimal for. Okay, so what is my subset here? My subset is 3 and 4. And I can say this is the optimal subset. What did I write? Subset, that's fine. Among items 1 through 4. Two, 3, and 4, when the capacity is 10. Okay, so let's chew on what's happening with these. Okay, and we can get them into one picture. So what I did was I said, let's start with an optimal subset. Right, look at the top of the screen. And let's describe an optimal subset for the original problem. Now let's figure out a subproblem of my original problem, which results from removing one of the items from my optimal subset. So if I remove an item from the optimal subset, the question is, what is the remaining stuff optimal for? And the answer is, it's optimal for the problem I've described below. Okay, so one of the interesting sub-problems to the knapsack is what you get when you remove an item, like you remove access to an item, and you remove its associated capacity. Okay, so that's really the core of the DP idea that we're going to be applying going forward.